Hello everyone, I'm Louis Del Monte and welcome to Del Monte on Science. Today we're discussing the universe's accelerated expansion. This is part 4. I did make a minor mistake in the last posting saying that we were going to go to part 3, and actually that was part 3. This is part 4. It should have said we're going to discuss what's going on with distant galaxies in part 4. So let's talk about that. All right, what we're seeing, if you go by what Hubble observed, you take the Earth, this is the Earth, and you look at a distant galaxy, and I'm going to put one here and one closer. The further away a galaxy is from the Earth, the faster the velocity is that it's expanding away from the Earth. So V1 is greater than V2, so V1 is greater than V2. And if you look at very distant galaxies, V1 can actually exceed the speed of light, can appear to exceed the speed of light. Now, what I explained is that it's the space between galaxies that's expanding faster than the speed of light, not the galaxies themselves that are moving at the speed of light or faster than the speed of light, because that's prohibited. No mass can actually travel faster than the speed of light, which is prohibited by Einstein's special theory of relativity. Now, if we think of a vacuum as a collection of virtual particles or energy, and whether we talk about particles or energy, they're equivalent, because in Einstein's special theory of relativity, E equals mc squared. So you have a mass-energy equivalence. And we know vacuums, perfect vacuums, contain energy. There's no question that that's the case. And what I explained was happening is that the size of this vacuum is constrained by gravity. And essentially, if you look at the force of gravity, and I'm just using Newton's force of gravity right now because it's a little simple and it does illustrate the concept. You can get into relativity and look at it from a different viewpoint. But here you have a collection of particles or energy, and that one particle is drawn to another. It's an attractive force. So it's the attraction between two particles, and here's mass 1 and mass 2. And so you get an attraction, and this is the force of attraction between the two particles. And as far as we know, gravity is always attractive. Now you'll see that people will talk about negative gravity and things like that. There's no scientific proof of that. We have not seen any case, and even with particle accelerators, in which we see negative gravity, things being pushed apart. So gravity is always attractive, and so this vacuum is, the size of it on a grand scale is constrained by Newton's gravitation, law of gravity. Now, as I remove mass from this, what happens? Well, the force gets weaker, so the gravity gets larger. Not the gravity, but the vacuum gets larger. So, when you have a planet, its size, like the Earth, its size is determined by the amount of mass and the gravity that holds it together. So this is important, that the density of virtual particles defines the size of the vacuum. So now we're ready to answer the 3 key questions. 1, what's causing the vacuum of space between galaxies to expand? And that is essentially that if these are galaxies that I've just drawn, in order to sustain their existence, they're pulling energy out of the vacuum of space. 2, why are the distant galaxies going away from us faster than those closer? The reason is that the distant galaxies have existed longer. So they've had more time Here's a distant galaxy. Here's a closer galaxy. Here's the Earth. This distant galaxy has had more time to pull energy out of the vacuum. And three, and this is a key one, why is it in our own galaxy we don't see space expanding? Here's our galaxy, okay, and there's all kinds of planets in here, and here's the Earth, and here's the Sun, which is very large. I'm not drawing it in proportion, but we don't see any expansion of space within a galaxy. Why is that? Well, I have a postulate, and the postulate is that galaxies contain dark matter. Okay, and we really don't know what dark matter is. Some postulate, we know it's real, and we know it's real because we can see that it bends light. And we know it's real because if it wasn't real, the outer stars of a galaxy should be moving much slower, or they would be thrown into outer space. And this has been known for a very long time, that basically the outer stars are not moving slow enough. They're moving with the same speed as inner stars. And that is only possible if there's more mass than we could see. And since we can't see it, we call it dark matter. I believe it's this dark matter that makes the galaxy act, if you will, like a single mass. Effectively, it's a single mass. And so it's gluing everything together, in effect. And that's a postulate. I can't prove that. No one has been able to actually prove what dark matter is. We've been looking for what's called the WIMP, a massive, slow-moving particle. But Fermilab has not been able to detect it. No one's detected it. And so it's very likely it's not a particle. It's not predicted by the standard model of particle physics. I suggest in the book that we may want to look at dark matter being some form of energy. But whatever it is, it's clearly making galaxies behave like a single mass rather than individual planets and stars, etc. It's acting like a single mass, pulling energy out of the vacuum between galaxies. So that is the whole theory. Thank you for joining me in this set of 4 on what's causing the accelerated expansion of the universe.